Today's lesson is solving by substitution, which is lesson 4-2. Our driving question: what does it mean to solve a system using substitution, and how does it connect to solving by graphing, which was our last lesson? So I'm pretty sure you're familiar with the word substitute. Substitute means to use in place of. So we can solve a system using substitution if we first isolate a variable in one equation and replace it or substitute it into the other. But let's look at what that means. Okay, so here we have example number 1. Sometimes a variable will already be isolated for you, which is pretty nice. So here's my system. I have y equals negative 2x plus 5 and 3y equals negative x minus 5. So notice that one of them is already isolated for us. So we can rewrite the equation, the second equation, as 3, and then instead of y, I'm going to put negative 2x plus 5 in place of. There's that definition of the word substitute. And then of course I'll rewrite the rest of the equation the way it was, negative y minus 5. I do have to distribute that that 3, so I get negative 6x plus 15, and that's still equal to x minus 5. Now I want to get all my x's on one side and all the regular numbers on the other, so I'm going to move the 6x over, but it'll be positive on the other side, and I'm going to move my negative 5 over, and it'll also be positive on the other side. So now I have 15 and 5 together on the same side. That's 20. On the right hand, I had negative x plus 6x, that's 5x. And of course, to get x completely alone, I divide by 5. So x equals 4, which is great. That's part of my answer. But we know that when we're solving systems, the answers are a coordinate point. I have the x coordinate, but not the y coordinate. So in order to find that now, I can take my answer and put it into the isolated equation. That's what I like to call it. And that's how we're going to solve for y. So my isolated equation was y equals negative 2, and then instead of x, I now know that x is 4. Once again, I'm substituting. So negative 2 times 4 is negative 8, and plus 5, I get y is negative 3. But I don't want my answer written like that. I actually have to write it as a coordinate point. So my answer is 4, negative 3. That's the coordinate. That would be the intersection point on the graph. But this time I did it without graphing. I did it using substitution. So once again, how can we check our work? I'm not actually going to go through and figure out what the work is, but remember, the way that you do that is to take your answer for x and y, plug it into the equations, and make sure that the left and right side match. If you don't remember how to do that, you might want to look back at your notes or re-watch the video that's lesson 4-1, and it shows how you can check your work. So now for the second example. In this example, there's not one variable that's already isolated for us, so we need to isolate one. It doesn't matter if it's x or y, we just get to pick one. But I will say there's normally like an easiest variable that we can isolate. In this specific problem, I noticed that x is already looking kind of lonesome there. It's by itself. So if I can just move over that negative 2y, then I'll have x isolated. Remember that when it crosses through the equal sign, it does change from a negative to a positive. So instead, I'm going to have x equals 2y minus 4.5. So now, as we did in the last example problem, I'm going to rewrite this time the first equation. It's whichever one you didn't isolate. So I'm going to rewrite the first one as 2. Instead of x, I'm going to substitute in a 2y minus 4.5. I still have my plus 3 equals 12 there. I have to distribute the 2. We have 4y minus 9 plus 3y equals 12. We do have to combine like terms, so from that 4y and 3y, that's how we got 7y. and then that minus 9 equals 12 is still there. We're trying to isolate y now, so I have to move over that negative 9. It will turn into a positive 9. So I have 7y equals 12 plus 9, which is 21. And then divide by 7 to get y alone. So y equals 3. Once again, that's only part of our answer because we need an x and a y value in order to have a coordinate point. So I take my answer for y, which was 3, and I plug it into what I called the isolated equation, the one that already had x alone. But instead of y, I'm going to put in what I know y is, which is 3. 2 times 3 is 6, and 6 minus 4.5 is 1.5. So now that I have both my x and my y values, I can write it as a coordinate to get my final answer, the solution. So this time it's coordinate 1.53. On to the next example. Example number 3. So in this problem, we have 6x minus 3y equals 15, and y equals negative 2x minus 5. I already have one isolated for me, so I'm going to rewrite the first equation. Substitute what I know y is, so instead of y I'm putting negative 2x minus 5. And I'm going to try and solve for x. When I distribute that negative 3, I have 6x minus 6x plus 15 equals 15. And you notice that 6x minus 6x, they cancel each other out. So I'm left with only 15 equals 15. That's not much of an equation, and obviously 15 does equal 15. So when we get this answer, that means that there's infinitely many solutions. And we had answers that look like this in the first lesson as well. So, well, the other day in the first lesson, we had infinitely many solutions when the graph was right on top of one another. So let's see if that's true in this case. For each one of the equations, I want to get it into y-intercept form, slope-intercept form. So I have to isolate y. I want you to follow along with my work. Definitely write it down if you have to. But that first one, we end up with y equals 2x minus 5. And the second equation was also 2x minus 5. So because they're the exact same equation, that does mean that one line was overlapping right on top of the other line, which is why we have infinitely many solutions. And a final and fourth example. So in this one I have the two equations, 2x minus 6y equals 12 and 3y equals x plus 6. I want to isolate one of the variables. I saw that x was almost completely alone, so I solved for x. I'm now going to take what x is equal to, the 3y minus 6, and substitute it for x in the first equation. Once I distribute the two, I get a 6y minus 12 minus 6y equals 12. Once again, 6y minus 6y, they cancel one another out, and I'm only left with negative 12 equals 12. The numbers are the same, but one's negative and one's positive, so they're actually not the same value. It's not like example 3 where it was 15 equals 15. Now it's negative 12 equals positive 12. So since those two are not equal, this is impossible. We just write no solution. We don't have any possible answer here. When we solved by graphing the other day, we saw that the only time that we had a no solution problem is if the two lines were parallel. So I went ahead and got it into slope-intercept form, each one of these equations. You can look at the work that I showed there. But you'll see that the first equation ends up being y equals 1/3 x minus 2. and the second one is y equals 1/3 x plus 2. So they have two different y-intercepts, but the same slope. So when we have the same slope, two different y-intercepts, the lines are parallel, they'll never have an intersection, and therefore it's no solution. So please make sure that you go back through all of these, make sure you have all of the notes down, the different examples, write any questions if you have some, so that way you can ask me during class. And then here